Good afternoon. Today we're going to talk about solving absolute value inequalities. We're also going to touch on what compound inequalities are. Hopefully by the end, we will know how to solve absolute value inequalities. And we will know how this process is different from solving linear and absolute value equation. I'm going to shorten that there. Need to work on my EQ. All right, let's start by talking about compound inequalities. A compound inequality could look like this. It's an example. The example says that x can be greater than -4 and x can be less than 3. So in this particular case, the x values that satisfy both of those inequalities lie between the numbers -4 and 3. This is what we call an AND inequality. I also sometimes think of this as a sandwich because all of the solutions are sandwiched between those two numbers. An OR compound inequality would be something like I can be less than -3, less than or equal to -3, or x could be greater than 1. In this particular case, this is a split. So sometimes I say that this is a split. And just to be consistent, this was my sandwich because my solutions were sandwiched between the two numbers. And in this case, the solutions are split between the two numbers. And this is created by an OR statement. The way we solve these, notice, and I just want to take a moment to point this out. In these examples with common inequalities, there is no absolute value symbol. So these are just inequalities, much like what you would have encountered in Algebra 1. We'll get to the absolute value inequalities in just a moment, but it's worth talking about because this sort of lends itself to what we're going to learn about absolute values. In this particular case, I notice that my variable is sandwiched between two numbers. That makes it an AND statement. To solve this, I solve it the way I would solve any equation. I'm going to solve for y. And the only thing I need to remember is that when I'm working with inequalities, if I multiply or divide my inequality by a negative number, then I have to flip my inequality symbol. Otherwise, we're good to go. What I want to do is isolate my variable, and I'm going to use order of operations sort of in reverse order to do that. I'm going to add 7 to all parts of this inequality. And I end up with something that looks like 15 is less than 3y, which is less than or equal to 30. From here, I'm just going to divide all my parts by 3. And I end up with a simplified inequality that looks like 5 is less than y, which is less than or equal to 10. And I can graph this inequality if I want to. I'm going to place my numbers on a number line. Notice when I go to graph this, my number line doesn't have any pre-created numbers on it. Therefore, you get to decide where the 5 and the 10 go. They do not specifically have to be measured out 5 spaces apart. You can put them anywhere that works for your brain because because you're the gods and goddesses of the number line. So I put my numbers because they represent the bounds by which all y values are between. I remember that when I'm using a less than symbol, I'm going to put an open circle. And I would do the same thing for a less than or a greater than symbol gets an open circle. That means that I can get very close, infinitely close to the number 5, but I will never actually be equal to 5. On the other end, I notice that this is a less than or equal to, and in this case, I'm going to use a solid endpoint. So on my 10, I'm using a solid point. And I do that for less than or equal to, or for greater than or equal to. And that just harkens back to, gosh, long, long ago. This is the solution set written as an inequality. To graph that solution set, I want all points that are between 5 and up to and including 10. So this number line is exactly the same, it represents the same y values that this inequality represents. Let's look at another one. A compound inequality that uses an or statement might look something like this, and it literally has the word or in the statement. And in this case, what I need to do is I need to solve both equations. And I'm going to solve them independently. For this one, I'm going to say k plus 6 is less than -4. I'm going to subtract 6 from both sides, ending with a k value that has to be less than -10. This is one possible set of solutions. The other possible set of solutions would be 3k is greater than 14. I'm going to divide by 3 because we solve inequalities in a very similar manner. This is a simplified improper fraction, and fractions are not the enemy, so I'm going to leave it as 14 divided by 3. It's going to be easier to graph this way, I can promise you. And now I have a solution set. So what I want to show here is that my or statement, it created a split solution set, whereas my and statement up here created a sandwich solution set. Hopefully that makes some sense. So now I'm going to go ahead and I'm going to graph my points. And when I graph my points, I'm first going to start with the -10. And again, you get to put that -10 anywhere you want to on your graph. My upper bound, or the values of k, have to be greater than this number. So I'm going to write 14/3 here. I'm going to check and notice that both of my inequality symbols are just less than or greater than. So I'm going to use open circles for those. I'm not going to do it in any strange color. Open circles for both. And then to graph my solutions, I want to highlight all numbers that satisfy this statement. So I think in my head, what's a number that is less than -10? And that would be a -11 or -12 or any number that continues towards -infinity. For this particular one, what's a number that's greater than 14/3? Well, 15/3, which is 5, would be greater. 6 would be greater. So I'm going to highlight all the numbers that are greater than 14/3. And that's how we can graph and solve compound inequalities. Welcome. In this lesson, we're going to talk about absolute value inequalities. We're going to use the definition of an absolute value to solve some inequality statements, just like we did when we were solving equations. Typically, there are two different cases. For the first one, if I look, the absolute value of A can be less than some number B, which means that it has to be on the number line. The distance between A and 0 has to be less than B. The other case, when the absolute value of A has to be greater than B, that means that the distance between A and 0 on a number line is going to be bigger or more than whatever number B reference. That's kind of hazy. Let's look at some specific examples because I think that makes it a little bit more solid. And if you can, as you're solving inequalities, if you can go back and think to yourself, what does this inequality mean in the context of this absolute value? I think it'll be easy to see, or easier to see, what kind of solution set am I going to end up with? Am I going to end up with a sandwich or a split? I look at this one. This says the absolute value of x has to be less than 3. That means the distance from x to, or the distance that x has to be a number that is smaller than the distance between 0 and 3. So if I put on my number line 0, 1, 2, 3, the absolute value of whatever number this is has to be between these two because it's going to be less than 3. But we also know that with absolute value that my number can be less than absolute value of my number can also be between -3 and 0 because the distance between 0 and -3 is 3 units. So when I say the absolute value of x is less than 3, I'm talking about any number that lies between those two endpoints. So if I think about it, I'm going to just highlight this a little bit. from -3 to 0 is 3 units. This distance is 3 units. The distance from 0 to 3 is 3 units. So x can be any number that lies in between those two, because that number by force has to be less than this total distance. Okay, so that's what it means. All numbers between -3 and 3 are going to be less than 3 units away from 0. And if I write that as a solution set, I would just write something like -3 is less than x, which is less than 3. Or if you wanted to, you could use interval notation and write it like this. What I have noticed here, and well, I've noticed that I created a sandwich. I can test it. What's the absolute value of -2? Is that less than 3? Well, the absolute value of -2 is 2. -2 is 2 spaces away from 0. So is 2 less than 3? Yes, it is. So it works. I'm going to test another one. What about -4? Is the absolute value of -4 less than 3? Well, -4 is 4 units away from 0. And so I have to ask myself, is 4 less than 3? And the answer is no, it's not. So -4 or +4 for that matter would lie inside my solution set. I'm going to go ahead and highlight this because that is my solution set. And so that's what an absolute value inequality can look like. There's another possibility. What about an absolute value of x that is greater than 5? Let's think about that. Whatever's inside my absolute value grouping symbol has to evaluate to a number that is greater than 5. So if I put 0 on my number line, I'm just going to squeeze these together a little bit. So my number inside of here has to be bigger than 5. That's what this inequality is telling me. So again, if I do like I did up above, the distance from 0 to 5 is 5 units. And whatever the absolute value of x is, it has to be more than that 5 units. So I know that my solutions have to lie out here. But we also know that from 0 to a -5 is 5 units. So there's another part of this solution because the distance from 0 to -5 is 5. So I could possibly have a number that lies in this area of the number line that still satisfies this inequality. Take -6, for example. The absolute value of -6 is 6, right? The distance from -6 to 0, that's 6 units. Is 6 greater than 5? Yes, it is. So -6, and for that matter, 6, would lie inside our solution set. What about 4? Is the absolute value of 4 greater than 5? Well, 4 is 4 units from 0, and therefore it is not greater than 5. So in this case, I would think that 4 should not be part of the solution set, and it's not the way we've drawn it here. If I want to represent the solution set in a way other than using a number line, I would say something like, let's see, if I use set builder notation, I want values of x such that -5 is greater than x, or, because there are 2 different possibilities, this is a split, or x has to be greater than 5. And those are my 2 possibilities. If I want to use interval notation, which I'm sure you're asking yourself, because Ms. Palmer loves interval notation. If I'm using interval notation, then I know that my x values can go in a negative direction infinitely, but they stop at 5. And if I were being really precise here, I would put circles here, and I absolutely should. I can't actually, because this is greater than, I can't actually touch 5. I have to be greater than 5 units away from 0. So this represents the left-hand side of my graph. And I put this capital U looking thing, that's notation, interval notation. It means or. That's kind of a fancy schmancy thing. So this is one half of my solution set, and the other half of my solution set starts at the number 5. It doesn't touch it, so I'm using a parenthesis, and it continues infinitely in a positive direction. So both of these are the same representation for the number line I've drawn here, and they're the same representation, or they represent the equation absolute value of x is greater than 5. All right, so you need to know about graphing and finding solutions to inequalities. The next question is, how do I get my equation in such a nice simplified form where it's a little bit easier to read? That's where the solving part of the lesson comes in. So now we're going to talk about what does it mean to solve an absolute value inequality that's a little bit more complicated than what we just saw. Well, there are some defined steps. The first thing we need to do is we need to think about what our solution set is going to look like. So is it going to be an and statement, or is it going to be an or statement? It will be one of the two. Either my solutions live between the two endpoints, or they live outside the two endpoints. Okay, so there is a generalized rule that you could probably surmise from looking at the equations up above. But if my if symbol is greater than, then I am going to live outside my bounds, and this is going to be an or problem, just like number 4. If, however, I have a less than or equal to, so if I'm less than, then that is going to create a sandwich or an and problem. And my solutions are going to live in the intersection or inside those two solutions. And then we will talk later about what special solutions are. We're not going to worry about those for the moment. Let's try an example so that we can make this a little bit more attainable. The first thing I notice is that this is a greater than symbol, so I know this is going to be a split. And we'll talk about how to think about this in just a moment. The first thing I want to do is I need to isolate my absolute value. Isolate, I teach math. I need to isolate my absolute values, right? Which is what we did when we were solving equations. To do that, I'm going to add 10 to both sides. And I end up with the absolute value of 2x minus 3 has to be greater than positive 5. Okay, so for a moment, just work with me. Let's ignore what's inside the absolute symbol. What we talked about up above in example 4 is that whatever this evaluates to has to be greater than the distance from 0 to 5. Or the distance from 0 to negative 5, right? Because I want whatever's inside of here to evaluate or to a number that is greater than 5 units away from 0. That's what the absolute value symbols tell me. That doesn't mean that those are the solutions, but it does tell me that whatever it is, it's going to be split because I have to be greater than 5, greater than negative 5. Okay, so when we have this kind of situation, we're split the inequality. And we know from looking up above, whatever's inside my absolute value symbols, I want to put that there, whatever's inside of here has to be less than negative 5. Because I have to be more than 5 units away from 0. The only way I can do that is to be a number that is less than negative 5. Or, just like we talked about above, or my absolute value, whatever's inside my parenthesis, or inside my absolute value symbol, has to evaluate to something that's greater than 5. Okay, because I have to be, whatever this is, has to be more than 5 units from 0. So that's how we set up this split. Notice when I have the negative distance away from 0, I want things that are smaller than that because I want them to be greater than 5. And so I end up adding a negative and flipping my sign. Don't think you need to worry about that. I think if you just think about what inside has to be more than 5 units in either negative or positive direction, you'll figure it out. All right, so from here, we just solve our equation the way we normally would. This gives me 2x is greater than 8, or x is greater than 4. This equation, if I add 3 to both sides, gives me 2x is less than negative 2, x is less than negative 1, and I'm still carrying this or statement here. And I can graph this. So when I graph it, I'm going to put my numbers somewhere on a number line. Let's see, I'm going to start with 0. Here's negative 1, and here is a 1, 2, 3. Woo, look at me, I was almost right. It is a greater than symbol. So greater than symbol, I'm going to use an O circle. And we know that this graph is split. So I'm going to recognize that the numbers that are greater than 4 live to the right of 4, and the numbers that are less than negative 1, negative 2, negative 3, all live to the left of negative 1. So this line represents my solution set. And I can write this solution set. I can say that the solution set are the values of x such that negative 1 is greater than x, or x is greater than 4. I could also write this using interval notation and say that my solutions go from negative infinity to negative 1, or they go from 4 to a positive infinity. And both of those are good representations of my solution set. All right, let's try another one. The first thing I know is that I need to isolate my absolute value, which has already been done for me. The next thing I recognize is that this is a less than or equal to symbol. So no matter what's inside my absolute value symbol, it has to be less than 14 units away from 0, either in a negative direction or in a positive direction. Whatever is inside of here has to evaluate to something that's less than 14 units away from 0. All right, so I know that that is going to, if I were just to draw a picture up here, and this is not my solution set, but this is just what this means. Here's 0, here's 14, that's 14 away, and here's another negative 14. So my solutions have to be less than the distance from 0 to negative 14, or less than the distance from 0 to 14. So they're going to lie somewhere in between those two numbers. That creates an AND statement, or a sandwich. And when I create my sandwich, what I'm going to do is I'm just going to think, okay, I know that negative 14 is the smallest number that I can get to. And whatever's in here has to evaluate to a number that is either bigger than negative 14, or it has to be less than positive 14. And that's just going back to what does that absolute value mean? From here, we can solve this the way we would solve any inequality. I'm going to divide all my pieces by negative 7. And see, this is a compound inequality now. And this is the connection we had to the previous page. So we are solving a compound inequality at this point. Negative 14 divided by a negative 7 is a positive 2. I have my x, and positive 14 divided by negative 7 is a negative 2. You'll notice I didn't put in my symbols. And that's because I'm remembering that when I divide or multiply an inequality by a negative, I have to flip my signs. And that is going to be something that occasionally trips me up, and it might trip you up too. But just being cognizant of doing by negatives, multiplying by negatives can help that process. All right, so this is kind of jumbled. I prefer looking at it as negative 2 is the x values, which are less than 2. Again, it's a sandwich like we said it was going to be. It's not the same as this one up here, because this one is what we were thinking of up here was the entire expression inside of here, not the actual value of x. So I'm just going to throw my negative 2 and my 2 down on my number line. And I'm not spacing those out consistently, but we're going to give it a go. I messed up here. This is less than or equal to, so I'm going to go back and just double check to make sure I've got the right kind of endpoints. These are solid endpoints because they are less than or equal to -2 and +2. And I recognize that my solutions are all of the numbers that lie between them. I can check myself. -2 times -7 is a +14. Is 14 less than or equal to 14? Yes, it is. I can check with 0. Is 0 times -7, which is 0, is the absolute value of 0 less than or equal to 14? Yes, it is. So I know I've identified the correct solutions. Finally, I need to write this inequality statement. I have a good inequality statement here. I can keep that one. I could write it as in set builder notation, which really looks about the same. X such that -2 is less than X, which is less than 2. Or I could write it as an inequality or as an inner notation statement, which is just -2, 2. You can choose the method that makes the most sense for you. All right, before we move on and start talking about special solutions and how to write absolute value equations, I wanted to tell you a joke. It's a dad joke. Here goes. What did the fish say when it ran into a wall? Damn. Okay, there you go. Dad joke for the day. Let's move on and talk about special solutions. So special solutions are those weird cases where you either have no solution or you have infinite solutions, and hopefully you remember some of those from when we had systems of equations. Similar things can happen with absolute value. I can have no solution. That's what this case would evolve to. And you're probably asking, why is the absolute value of A not ever going to be equal to -B? And that is because we actually, remember, if you remember, A, the absolute value of A is the distance from 0. And distances can't ever be negative. So since I can't ever evaluate anything in here, the distance from 0 will never be a negative number. If you end up with an absolute value of -7 equals -5, then you automatically know that there is no solution. Similarly here, if I can't be equal to a negative, then I certainly can't be less than some random negative number. Absolute value of A will never be less than -5. So this again is no solution because, whoops, need that in there, because the absolute value of A can't, again, be, and in this case, it's less than, or I would say it really can't be less than 0, or it can't be less than a negative. We just can't be, we can't be negative. You'll never evaluate to a negative. And then lastly, in this particular case, this is asking, is there a number that is greater than -3? Or is the absolute value of something going to be greater than -10? And the answer is always, and that there's an infinite can't spell and talk at the same time. Infinite solutions, because all numbers, the absolute value of any number you can think of is always going to be greater than whatever this negative number is, and that's because distance is always a positive number. So I would say that the absolute value of A is always, and I emphasize that with a horribly unmelodic sound, but this will always be positive. So those are some special solutions. If you get to the absolute value of 2x minus 7 is less than -3, you can stop. You don't even have to solve that because you know there's not going to be a solution. All right, let's talk about how to write some absolute value equations. There are some steps you can go through that will make the problem a little bit easier. the first thing we're going to do is we are going to place the central value, and I'll tell you what that is in a minute. We're going to place the central value inside some absolute value bars, and then we're going to try to figure out what the range is, and the range is what my absolute value equation is going to be equal to. I solve it, whether it's an absolute value equation or an inequality, I solve it using the steps we've already spoken about. And then I check to see if there are any extraneous solutions. Let's do an example. Most tennis rackets have a 110-inch square head. That's the part that has the net. It's going to be about this size because most of them have this size. This is my central value because it is where most rackets end up being. So I'm going to call this my central. Anything that deviates from 110 would have to fall within our range. And that's the next number that's given. It says plus or minus 25 inches. That means I can be 25 inches smaller than this. I could be 25 inches larger than this. But most rackets will not be outside of that range. Okay, so having identified those two numbers, I can write an absolute value equation. So the racket I have minus my central value, which in this case was 110, has to be, the absolute value of that has to be within a 25-inch squared range. So that's the equation that I set up. Now I use my solving equation skills. I remember that there are two situations that I must allow for. The first is where there's a negative range, and the other one is when there is a positive range value, in this case the 25. I solve it using my normal skills, and I end up with x equals 25 or x equals 135. And I'm going to put in big bold letters here the word or, because it can be the smallest value. That's what it was asking for. It asked me for the least. So the smallest bracket, smallest racket head will be 85 inches squared. The largest, let's find a good color here, or the greatest racket, the greatest racket head, again, can't write and talk. The greatest racket head will be, as we discovered, 135 inches squared. So this is the smallest, this one's the largest. There might be racket value, size values that are between those two numbers, but this problem asks us to identify what this was, what the smallest was. You can't see that. I will raise it up. I like to write my answers in some sort of sentence form, so I'm identifying exactly what these numbers are. It gives them meaning, and it is a little bit easier to interpret. That's it, folks. Thanks for your attention.